It's my great pleasure to introduce the first keynote speaker for today, which is Aaron Klein. He's currently a research group lead at CATS AI at the University of Leipzig, and prior to that, he was a senior scientist at AWS. And before that, he completed his PhD at the University of Freiburg, where we actually started our PhD together. And many of you will know him from his work on SignTune and contributions to SageMaker, and also as a host or one of the hosts of the AUTOML seminar. And today he will discuss how we can compress large language models. Please join me in welcoming our speaker. Stage is yours.
Thank you. Thank you for the nice introduction. And well, thanks for having me. And thanks for organizing this great conference here in Paris. After living now almost 5 years in Berlin, I really do appreciate how clean and organized Paris is. So yeah, welcome to my 45-minute rant about my love and hate relationship with Berlin. Now, today I'm going to talk about neural architecture search and how we can use it to compress large language models. And in this talk, I'm not going to present you any new NAS methods. So all of the methods I'm going to talk about, you might be familiar with or you have heard them before. So they're very well known in the literature. But I'm going to present you a new practical application or an important use case for NAS, where NAS can have a significant impact in the context of large language models. So why is this an important use case? Well, because there's this recurrent criticism of large language models that they have this enormous hunger for computational resources. And with this hunger for computational resources, it comes obviously a lot of enormous energy consumption. And if you happen to run a 10 billion startup, you at some point also have to worry about how to monetize your large language models. So you need to reduce essentially your cost. And this is not just for training, which right now probably consumes most of the computational resources, but also for inference, right? Those models are very successful. So we're right now deploying them more and more in production and all kinds of different services and so on. So the amount of inference cost is just going to increase in the next couple of years. And the inference cost is maybe at this point still lower in training, but in the foreseeable future, this might even supersede the training cost that we're currently spending. Just to give you an example, so when I was still at Amazon, I was part of the science team of Amazon Q. Amazon Q is essentially the AI assistant, an LM-based AI assistant of Amazon. So think of it essentially as the ChatGPT of AWS. What is an AI assistant? An AI assistant essentially is a chatbot that allows you to answer any questions about AWS, but it also allows you to execute certain commands. So for example, you can ask it here how many EC2 instances you have, and then essentially it generates a piece of code and executes it and then lists all the EC2 instances. And in such a system, there's not just one large language model that you invoke essentially, but it's a complicated pipeline where different parts of the pipeline consist of large language models. And potentially different large language models, so it's not necessarily always the same, but you know, you have to create them multiple times. So just to give you an example, so if a user comes in and sends you a prompt, you might first need to do some input checks or input guardrails. So essentially you check whether this prompt contains some toxic or malicious prompt injection attack or something. And that's the classical classification problem, right? You have text and you want to classify whether it's malicious or not. And this can be efficiently solved by large language models. Usually you don't use a very large model, maybe something like 7 billion or even smaller. Sometimes also encoder-based networks such as BERT. But it's a typical classification problem. And then, well, let's say the prompt is valid, you send that to another large language model to generate code. And that's usually a much larger model. So now before you can actually execute this code, you might need to verify it, right? You need to run some tests. And maybe it's not valid, so you have to regenerate it. And that's so essentially it's a loop here. And then you execute this code and then potentially maybe have some output guardrails as well. So you want to check whether this prompt the text that was generated by your LLM doesn't contain, for example, any toxic language or anything like that. And you can see like in this pipeline, right, that just the amount of inference cost or the amount of inference time here essentially accumulates. And that essentially all adds up to the total response time your user has to wait until they get a response back. And obviously, the more complicated this pipeline becomes, so essentially, this inference cost is just going to increase. So what can we do? Well, there's a huge body of work right now in the literature how to make inference more efficient. One very popular method, for example, is quantization, where you essentially change the position of your weights. There's distillation, which is also a very popular method that's been well known in the literature for, I don't know, 10 plus years. We essentially train a student model to match the predictions of a larger teacher model. Then there's pruning, which is probably even older, where you essentially remove different parts of your neural network. And now in this talk, I'm arguing that neural architecture research can be another tool in your toolbox to make inference more efficient. I don't necessarily see this as a contender or competitor to all the other methods. It's more like a combination of those methods, right? It's a combination of pruning and some elements of distillation. And I hope to see in the future also combining it with quantization. And as a matter of fact, there is actually already a paper here at this conference that explores this direction. So what is neural architecture search? So most of people are very familiar with this, and I'm just going to explain it on one single slide and a very high level. But if you're keen to understand it more, then please, maybe you want to check out the tutorial later by Jovita and Gabriela. So essentially the idea is you want to automatically find or design new neural architecture search, right? So right now it's still very much a process of manual labor, so and often requires a lot of trial and error. But we want to automate this by casting it as an optimization problem. And essentially you give it some search space that you usually have to define, and then you would like to find the best architecture in the search space. Now that requires to have a search strategy. So in the past, it was, for example, evolutionary algorithms or reinforcement learning, Bayesianization, and all kinds of different methods here, and some way to estimate the performance of an architecture. Now, the standard form or the vanilla form essentially is just to train this architecture and then validate it. That's obviously super expensive. And in the first work that used reinforcement learning, that required like, I think 6 or 7 weeks on 800 GPUs. But now there's a huge body of work to accelerate this process tremendously. And yeah, maybe you want to check out the tutorial later to understand that better. Now, NAS has been very successful, and there was almost an explosion of papers a couple of years ago. So this is a paper by Marius group, where you see the number of publications over the year. And well, this is until 22, so maybe it has flattened out a little bit right now, but it's still very much a highly active area of research at this point. However, at the same point, or more recently, actually, there has been some criticism about NAS coming from the machine learning community. Well, fortunately, we have this popular platform to express profound and deeply detailed scientific discussions called Twitter, where people essentially were ranting against NAS and saying, yeah, like it's dead, or we don't need it anymore, especially in the context of large language models. And well, you can say this is the usual noise on Twitter, but I think we as a community might have to take a little bit of this criticism more seriously, because the initial promise of NAS was effectively to find the next big architecture, like a big next transformer model, essentially, that's revolutionizing the field. But if you look at the current state-of-the-art models, well, for example, transformers or Mamba, they're all manually designed, right? They're not a product out of NAS. And especially in the context of large language models, we see that architectural design choices matter less than the pure parameter count, right? So if you want to maximize your performance, you just throw as many parameters at the problem as you can. It's effectively what our scaling laws say, right? That your training loss monotonically decreases with the parameter count. So it's still a bit of an open question how to design the search space, right? So, and how to find like the next big model. And well, maybe that's a bit of a controversial opinion here, but my personal opinion is that I don't think that's going to happen maybe in the next couple of years. So we're not going to deliver on this initial promise of NAS to find the next best transformer architecture. And I hope you guys are not going to hate me for this, but yeah, I don't see this as maybe happening right now. But having said that, so I still think that there is some interesting work going on right now. And also here, this conference, for example, Linus has this paper about einspaces, which I think very interesting. However, where NAS has been very successful is this multi-objective setting, right? Where you not just optimize performance, because if you look at other metrics as well, for example, latency or energy consumption, the picture changes, right? And biggest model is not the best model anymore. On the contrary, now in a multi-objective setting, you don't have a single solution anymore, right? You have a Pareto set of solutions. And here the picture is much more nuanced. And I think we as a community maybe have to communicate that better to the larger machine learning community, because my impression is that this hasn't been well understood yet. And one very specific example where I think NAS has been extremely successful is in this hardware-aware NAS setting. And we heard about this already at this conference, where you not want to find the next, like a new revolutionizing architecture, but you rather want to take an existing architecture and optimize it for a specific use case, like for a specific hardware in this case. This could be, for example, a mobile device or an embedded system or an endpoint in the cloud. So it's a much more practical setting rather than just, practical use case maybe, rather than just this more explorative setting. And I'm showing you here a picture of this once for all network. I could have shown equally some pictures from other papers. So for example, from Frank's group or from Samsung's group, where, it was very successful approaches that are also currently deployed in industry. And the rest of the talk, I'm going to quickly recap some weight chain-based NAS, and more specifically two-stage NAS, and as a methodology to essentially compile large language models. And then the rest of the talk, I'm going to show you how we can use those methodology to essentially make large language models more efficient. I'm first going to focus actually on those encoder-based networks, which are small, like BERT type of networks, and maybe not as interesting as like large decoder-based networks, but since they're smaller, they allow us to do very thorough experimentation and understand essentially the problem better. So I see this more as a test bed essentially for NAS. And then I'm talk about hardware NAS, our new benchmark for hardware NAS for finding better, more resource efficient GPT-2 types of models. And I'm also going to quickly introduce our new open source library, which essentially is a toolbox to do two-stage NAS approaches. And then in the end, I'm going to give you a quick overview of the current work we're currently doing right now, and where we're trying to scale this approaches up to very large models. Now, this is obviously joint work with a lot of people. So a lot of people from Amazon, well, half of them are not at Amazon anymore, but anyway. And University of Freiburg, so Frank Harder's group. A special shout out here to Weir, because she contributed a lot of the plots here and the experiments. And also to Timo and Abo, who helped a lot with the open source library. Okay, so a quick recap of what is weight sharing-based NAS. And as I said, I'm talking about one specific way of weight sharing-based NAS, just that everybody's on the same page. It's two-stage NAS. I think we've heard about this already in the previous talk. And honestly, I think two-stage NAS is maybe some approach that is maybe a bit more popular in the computer vision domain and not so much in this domain. But I think it should, right? I think it maybe deserves a bit more credit here. And the idea essentially is, instead of having this complicated, expensive optimization problem where you train each network from scratch, you only train a single network, and that's called a super network. And essentially, the idea of the super network is that it contains all the architecture in the search space. We're going to see in a second more how this is going to look like. And then essentially, once we have the super network, the search, this multi-objective search, becomes very cheap because we don't need to train those models anymore. We just need to validate them using a subset of the weights of the super network. So what is the super network? So essentially, a super network is a very simple toy example here, essentially, where we assume, okay, we want to optimize the hidden dimension of a single layer fully connected network. And we essentially assume that it's just a very tiny search space. You only have 4 hidden units, right? So the largest number of hidden units is 4, and the smallest one is 1. So the largest network in the space contains the 4 hidden units. And this is what we call the super network, essentially, or the largest subnetwork. And now we can essentially, to get a smaller architecture, we can just slice this network to get a smaller subnetwork. So essentially, all of the subnetworks are kind of included in this largest subnetwork, right? So the red guy here, for example, would be the smallest one, consisting only of 1 unit. And then there's another one with 3 units. Now, with the super network, you have this concept of weight entanglement, which essentially means that all the weights of the smallest networks are also embedded or included in the largest network. So that means you need to be, if you take this perspective in mind, that you not have a single network, but like a super position of networks, or like a superset of networks, you need to you make sure that you disentangle them somewhat, like they don't co-adapt during the training process, right? Because normally what we do in deep learning, essentially a stochastic gradient descent, we compute the gradients of all of the weights and then update all of the weights in each update step. But now with this super network training principle, essentially we don't need to want to co-adapt, we want to avoid that the subnetworks co-adapt, so we need to disentangle that. So essentially in each update step, we only update a subpart of the network, like one subnetwork essentially. And the most simplest form essentially is that in each update step, we sample a random architecture from our search space and then only update the weights that correspond to this architecture. Now, there are some more, there's some other strategies in the literature. So random sampling is just the one I'm explaining, but more popular is the sandwich rule, where essentially in each update step, you not only just update one network, you update the largest subnetwork, which essentially is the entire network, the super network, and the smallest one, and then one or two random subnetworks. And that's, I think, right now most popular approach that's currently used in the literature. And then on top, we can also use some ideas from distillation, where essentially we want to minimize the Kullback-Leibler divergence between the subnetwork and the supernetwork. Right. So in this sandwich rule setting, essentially we did a forward path for our supernetwork, so we get the losses essentially for the supernetwork, and now the loss for the subnetworks is not just the training loss, like the cross entropy loss, for example, but also the Kullback-Leibler divergence between the losses of the supernetwork. So essentially the idea here is we want to distill the entire knowledge of the supernetwork inside the smaller network, or make them very close to the supernetwork. So some sort of regularization, if you like. And essentially the nice thing here is that you get this for free, essentially, right? Because you just need to change the loss function. You can do it in place, so it means during the training process. So why does it matter? So this is, again, a very simple toy example where we optimize the single layer fully connected network on MNIST with at most 64 units. So it's again a simple one-dimensional search space with 64, between 1 and 64. And we trained, so those blue dots essentially means we trained all of those networks in our search space from scratch in isolation, right? So those are the different plots, and you can see there, you can see that the parameter count somewhat correlates with the validation error here. Now, if you do just take the largest network and train it with SGD, and then we slice the networks off to get the different subnetworks, those are the red points. And you can see those subnetworks are substantially worse than training them from scratch. Now, if you use the sandwich rule, the performance of the individual subnetwork gets much better, and it's very close to the networks from that we trained from scratch. And then using this in-place knowledge distillation helps us even more, right? Especially for the smaller networks on the left side of the plot here, they get very close to the one that we trained from scratch. It's not perfect, so there's still a little bit of loss here for at least for smaller networks, but that's fine, right? Because we tremendously speed up the optimization process, right? We only train a single network rather than training 64 networks. And fair enough, so if training the single network is a bit more expensive than training the largest network in the architecture in your search space from scratch, right? Because of the sandwich rule, but still it's orders of magnitudes faster than doing this full-fledged NAS search, essentially. Now, once we have the super network, the search essentially becomes, well, not trivial, but much easier, because we not only need to do the validation, right? We don't need to do any training anymore. And this two-stage NAS, I think it's very related to pruning. And I see this more like as a specific type of pruning, right? We want to find a subnetwork in our network and then prune everything else. And there are two different types of pruning. So there's unstructured pruning, where essentially you remove single weights out of your weight matrix. And unstructured pruning is pretty odd. I think it was initial works already in the 80s. And people reported quite high pruning ratios. So some people showed that you can prune up to 90% or even higher of your entire network with almost no loss in performance. The problem is, since you only remove single entries out of the weight matrix, you end up with a sparse weight matrix. And that's not really supported by your hardware, right? So your GPUs don't necessarily support sparse weight matrices. Also, your PyTorch or TensorFlow don't support it natively. So even though you make your model smaller, it doesn't immediately translate to lower latency. Now, there's this other concept of structured pruning, where you not just remove single entries of your weight matrix, but entire rows or columns. So you essentially remove components of your network, such as, for example, different neurons or different layers, and that you end up with still a dense matrix, but the dimensionality of the matrix just becomes smaller. So that immediately essentially translates to lower latency, and you don't need to change anything in your PyTorch library. So structure pruning and NAS are very related, but there's still some differences, and I think it's worth to keep this in mind, because in the structure pruning setting, what you normally do is you define a threshold on number of parameters. So you say, I want to prune 50% of my parameters, and then you score every component in your network, and then you remove everything essentially that is, until you reach 50% of your parameters. The problem with this approach is that I don't know how much I can prune, right? So I don't know what's the best pruning ratio. Maybe it's 50%, maybe it's 60%. I don't know. I just want to prune enough that my loss doesn't get too bad. So in NAS, however, because it's such a general framework, we can have this multi-objective setting, and we get essentially after our NAS the entire Pareto set, and then can do decision post hoc, right? We can just look at our Pareto set and pick the best solution that fits our use case. And the other thing which I think is worth pointing out is that since NAS is this, it's a multi-objective problem, you can just put in any metric you care about, right? You can immediately or directly optimize latency or energy or memory or all of them together. And that's something you often can't do with structure pruning. Structure pruning only looks usually at the number of parameters. And essentially, to extract the subnetwork, we put a binary mass over all the heads in our multi-head attention layer and all the units in our fully connected layer. So essentially, those binary masses, essentially, it's the dimensionality is the number of layers times the number of heads per layer. Right. So that's the idea, essentially. So the pre-trained network is now a super network. So essentially, we don't stiff into the standard NAS setting. We don't train our super network from scratch. We fine-tune essentially a pre-trained network. So we start from pre-trained weights. And then we can run a multi-objective search that is similar like in the standard NAS setting. And usually the entire network, the total fine-tuned super network is part of our Pareto farm, because that usually gives us the best performance. Now, we could do this also with standard NAS, right, where we essentially place those binary mass over our pre-trained network and then fine-tune essentially the remaining subnetwork in isolation. But that's obviously quite expensive. But I'm just going to show you later how that compares against as a baseline. And the weight sharing based NAS setting, essentially, this is just we fine-tune this pre-trained network and then validate our subnetworks using those fine-tuned weights. Now, the big question is obviously, how do we define the search space? And essentially, there are different ways to how we can define it. The most simplest way is just you define 3 different hyperparameters. So essentially, the number of heads for all of the layers, or for each layer, essentially, the number of units and the number of layers. So it's just a 3-dimensional space. And if the model grows, so if you have more layers or more heads per layer, essentially the dimensionality stays the same, right? You only have those 3 parameters. It's just your upper bound increases. Now we can make this more flexible by allowing a different number of heads and a different number of units for each layer. And that dimension obviously increases with the total number of layers we have. Then another space, which is mostly coming from the literature, is to only prune layers, right? So we have 1 binary per layer. It's a very simple space. So essentially, it's just it's just the dimensionality is just the number of layers you have, and you have just binary vectors. Then the most flexible search space, which is usually used for structured pooling approaches, is to define a binary for each head and each unit in our network. And that's a highly dimensional space, right? And it goes quite quickly with the dimensionality of your search space, with the dimensions of your network. Now, given those search spaces, how do the binary masks look like? So those are some examples for the head masks. And you can see essentially in the small search space, you always keep, so everything that's bright here essentially means we keep the corresponding head, and everything that's a dark color means we remove it. And so in the small search space, you always keep the first number of heads, just to make sure that's a bijective mapping. And you can see here the different patterns, how your subnetwork is essentially going to look like in those different search spaces. Now, obviously, since we're in the multi-objective setting, the question is, how do we evaluate actually our Pareto sets? And we just follow common practice, compute a hypervolume. For those of you who don't know what a hypervolume essentially is, you define some reference points here called called R. And then giving our Pareto set, which is here the different Y values, we can essentially compute the volume to this reference point. And so we want to increase it. So the higher this value, the better our Pareto set essentially is. First question we're going to look at essentially is which search space works better. And that's kind of interesting because the smallest search space, even for its very crude pruning, tends to work better. And it's a subset of all the other search spaces. So all of the configurations in the small search space are included in the medium or in the large search space. But given a somewhat reasonable budget, it's actually much more efficient to explore the smaller search space than this larger space. This large space is just way too expensive to really find something useful there. The layer space also works kind of well, but it's still a bit, it doesn't allow for very fine-grained pruning. This medium space is a bit more interesting because essentially, as I said, it's a more flexible search space than the small search space, but it turns out to perform actually very poorly. And the reason is that if you look at during the super network training, we sample configurations uniformly at random from our search space. Now, if you look at the distribution of our parameters of those subnetworks that we sampled uniformly from the search space, we end up with a very peak distribution of medium-sized networks. Because on average, we turn off half of the heads and half of the number of units. So on average, most of our networks are, we just end up with removing half of our components. So it ends up with a very biased distribution here, essentially. The small search space also have that problem a little bit, but it's not as severe as in this medium search space. Now, for the other two search spaces, we can change the sampling process a little bit to end up with a uniform distribution, but it's a bit more, we need to change that a little bit. We can't just sample uniformly from the space anymore. But since it's a binary space, we can sample more efficiently here, essentially. Now, next question is, we've seen that the super network training helps in this very simple toy example, but how much does it help actually in this more realistic setting here? And it actually does help quite a bit, right? So here you can see on the left, standard STD training. So we just fine-tune this entire network. And then we compare this against just randomly sampling and sampling also randomly, but increasing the probability of sampling randomly linearly. So we start with always updating the entire network and then just increase the probability during the course of training to sample a random network. That's also coming from the literature. And that helps a little bit, but the sandwich rule usually gets you the best performance. And we combine this now with in-place knowledge distillation. That's what's called full here. And that gives us the best Pareto sets, essentially. And there's quite a significant difference, right? So the super network training really does help to make our network more prunable, right? So if we just do fine-tuning and then prune it, the network essentially is not really prunable. So we need to do the super network training and to combat that. Well, the next question is obviously, how does it compare against structured pruning? Well, we compared against some methods from the literature. So you can see here, for example, this blue guy is head pruning. That's essentially what is like one of the default methods that's currently implemented in Hugging Face, and it actually performs very poorly here, right? So you can see on the x-axis the number of parameters that we have pruned, and the y-axis the test performance. And in this low regime where we only prune a small part of the network, so only 5% or 40% of the network, the structured pruning method actually works sometimes a little bit better. And because you can just do very fine-grained pruning, right? They operate in this large search space, so you can just remove single heads and so on. And that regime, we can't weight sharing based NAS, since we do this more crude pruning, we suffer a little bit of performance. But in this other regime, which is arguably more interesting, where you prune larger chunks of your network, NAS actually does substantially better than the structured pruning approaches, because they also can't really efficiently explore this search space, actually. We also compare here weight sharing based NAS, which is the green one, against standard NAS, where we train each subnetwork in isolation, but given the same amount of compute time, essentially. And in theory, so if you would run standard NAS long enough, it should always be better than weight sharing based NAS. But even for those benchmarks are fairly cheap. It's not super cheap, but fairly cheap. In a reasonable amount of time, it actually doesn't perform better. So we would have to would need to run it much longer, essentially, to catch up with weight sharing based NAS. So you can see it's essentially much more efficient in a limited compute time. Okay, but how does it help now in a more realistic setting? So first, I'll show you here essentially the latency of different parameter sets. So we found the parameter sets in the computer latency on different hardware devices. And you can see it reducing number of parameters also translates to lower latency. What's also interesting here, I compare this to against quantization, so 4-bit and 8-bit quantization. And while quantization helps tremendously to remove memory footprint, it doesn't necessarily lead to lower latency. I don't want to over-index on this because it might be a bit of an implementation issue. So I used here the Hugging Face implementation. But yeah, so it doesn't necessarily lead to lower latency. And again, I think it's not so much of a competition. I think in the future, we should look at a combination of quantization with NAS. Now, in a more realistic setting, we used those BERT models and deployed them as an endpoint on SageMaker. And then we essentially simulated the response time if a different number of users is querying this endpoint. And you can see here the red guy essentially corresponds to the unpruned network. And here and you can see the response time essentially increases with the number of users you have. And the solid line here is the median, and the dashed line is, sorry, the dashed line is the median, and the solid line is the, no, sorry, the dashed line is the mean, and the solid line is the median. And you can see that the discrepancy between those two increases. And the reason is because you see some following effects here. So essentially, at some point, if you have too many users querying at the same point, essentially SageMaker starts following. And that's why the response time actually, goes off the chart. And if we prune this network, essentially that immediately translates to lower response time, right? So you can see the purple guy and the blue guy in our parameter set deployed as an endpoint, and they have lower number of parameters, and they also have a lower response time. And here the mean and median are much closer to each other because here SageMaker doesn't throttle yet. So we haven't reached the point essentially of throttling. Okay, so next, so this is all for encoder-based networks. So how does it look like for decoder-based architecture, like GPT-2 type of models? And this is a benchmark that we just submitted to NeurIP's DPT track. Essentially, it's a surrogate assistant benchmark for hardware NAS on GPT-2 types of models. And this is mostly work driven by RIA. And we provide different super networks trained with weight sharing based NAS for 3 different search spaces consisting of different of a different size of the overall architecture. And we also provide some models to estimate the latency and energy consumptions for different hardware, for CPU and GPU hardware. And here, a big problem is that latency is a very noisy measurement, right? So, and it's often not Gaussian distributed. And the most estimators that are currently in the literature, they just give you a mean estimate essentially, but the mean is a very poor approximation of latency, right? Because you often have you have very heavily distribution with a long tail essentially. And so we put some effort into better calibrate those models to get a bit more faithful estimation essentially using AUTOML24. And yeah, as I mentioned, so we have different types of search spaces consisting here also of optimizing the embedding dimension. And here's a plot for a GPT-2 XL with 1.5 billion parameters, where we show the perplexity on the y-axis, on the x-axis, and the latency on the x-axis. Yeah, and you can see you get quite a rich Pareto font here of different subnetworks. And here you can also see that larger networks essentially doesn't necessarily, obviously also encode higher latency. When there's some sweet spot essentially where you still have a reasonable perplexity, but a much lower latency or energy consumption. Now, if you're keen on this and will say, cool, I would like to try this out as well. So good news for you. We have we just released an open source library for model compression of large language models. This is joint work with RIA, Timo, and Arbor. And if you're keen about this stuff, please do reach out to us. And it supports a variety of large language models. So it's based on LitGPT, and essentially we support the same type of models than LitGPT. For example, Llama 3, GPT-2, Pythia, and so on. But what I think what's really cool of this library is that it gives you the opportunity to checkpoint subnetworks, right? So if you look at the most pruning packages, where you can do all the pruning, but then you don't really what you need to what you want eventually want to use. If you want to use it, you want to deploy essentially the a subnetwork or a checkpoint of the subnetwork, and it's not so easy to get that, to extract that out of your super network. And we provide some functionality essentially to obtain those checkpoints, and that with those checkpoints we can then use things like eval harness to evaluate those models on downstream applications where you, in some in-context learning setting. Yeah, obviously we also provide some different implementation of all the super network training strategies that I showed to you here. And it's based on SignTune, so you can also use all the multi-objective methods that we currently have in SignTune. Okay, so the remaining time, I will quickly give you a quick overview of the work we're doing right now. So it's very much work in progress. And question is, how can we scale this up to larger models? And if you go to larger models like, Llama 3 and so on, we face some challenges. So the first one essentially is that right now we mostly looked at perplexity, but that's not what we care about, right? What we eventually care about is downstream performance using some few shot classification or like zero shot classification, for example, on some common sense data sets or on, alpaca eval or whatever. And well, technically we could just take those subnetworks, deploy them and evaluate them, but it's still expensive, right? It's not as expensive as training the trained model, but as I mentioned before, like inference can be also quite expensive. The question essentially, is there some better ways to approximate the performance of a subnetwork? And the other question is, okay, how can we fine-tune the supernetwork? So, in academic lab, we obviously can't full fine-tune anything that's larger than 7B. So is there another way to fine-tune our supernetworks? And large search spaces, what I mean by that essentially is going back to the previous slides, essentially, if you sample uniform our search space, and now the search space gets much larger, right? Because you have much more number of subnetworks in there. And we look at the distribution over parameter count, we see that we oversample in the regime with very small networks, right? So you can see here, I sampled here, I think 100 or 1,000 subnetworks uniformly at random from the search space, and look at their number of parameters. And most of those networks have 1,000 times less parameters than the original network. And those networks are often then too small to learn anything meaningful. So we need to bias this distribution a little bit more towards larger networks in order to find good Pareto sets. Now, if you want to, as I mentioned before, we can't fine-tune the entire network, but we can combine this with PEFT methods. Essentially, and that's very straightforward. There's already a paper about this called LONAS, where essentially, you just you take a super network, you use parameter efficient fine-tuning, for example, LoRa and so on, and then still do this super network training strategy. And that allows us to also fine-tune, like in this case here, a Llama 3.1, and to order to get this Pareto set here. All right, so with that, I'm already at the end. So hopefully I was able to convince you that reducing inference costs of large language models is a key problem. And I do think this can be a very important and practical use case for NAS that allows us to make like a significant impact in this large language model community. And I'm pretty excited about this two-stage NAS approach. I was very skeptical at first, I have to confess, but I think there is something to it, and it really allows us to efficiently compress these networks without, too much overhead. So essentially, it's not much more expensive than a single fine-tuning one. And those small encoder-based network architectures, like BERT and so on, they allow us, it's a useful test bed essentially for trying different NAS methods out there. So especially if you want to develop your new NAS method, maybe you want to first try this on the encoder-based networks first before you go to anything larger than that, to do very thorough experimentation. And especially, if you will for experimentation, we also provide this hardware GPT bench for you, which is surrogate assistant benchmark for multi-objective NAS for GPT types of models. Obviously, if you're keen in exploring this, check out our new library. And with that, thank you very much for your attention and happy to take any questions.